All right, everybody. So today I thought that we could take a little time and work through how to set up a large language model on an institution's HPC, or something where you have multiple different nodes that you would like to run a model across. Now, I think this is something that more and more places should be doing. It does cost money, but in the end, it's a lot more secure since you are running a model locally and you have a lot more control over what you can do. So maybe in the future, I'll talk about how to connect what I'm doing today, which is with vLLM, with something that is a front end, something like OpenWebUI or similar. Essentially, you just have to point those to the API endpoint that vLLM opens up. But yeah, I think it's something that more and more institutions should be doing. It is very expensive, so here's kind of my 2 cents. It's very expensive to also have everybody at your institution, whether it's a company or I don't know, company probably is the one that makes the most sense, hospital, have a large language model or something like ChatGPT that everybody can chat with and is secure. So one thing that we have to deal with is HIPAA, and you don't want to be leaking patient information such as their name or their identifier to a public model, because that's something that they might train on. If you don't want them to train on it, you have to pay their, I don't know, enterprise fee that says, hey, we can use you. You are going through all the checks and balances needed in order to make sure that what is coming in is actually locked down. You're not going to use it for training, but it's very expensive. And for an institution the size of the one that I work at, which is the cancer center, there's 10,000 people, 11,000 people that are working there. And if you get a license for everybody, that's very expensive. Copilot, I think Copilot Pro, aside from the Office 365, is $20 per person. It can add up very quickly. So I'll show you how to use something like the HPC. So at Moffitt, we have a fairly large HPC. We have actually a couple different HPCs. The one that I'll be using today is the one that's more general, that everybody has access to, just to stay away from the PHI HPC cluster. The one that I have pulled up here is we call red. I'm not 100% certain the story behind that one, but the HPC has 75 different nodes, and each of those nodes has 64 cores, a terabyte of RAM, and then an A30 GPU. So it was never really meant to run something like this, but we're going to give it a go anyway. The really nice thing about using vLLM, I don't have any slides or anything for this, but it allows very easily to set up a cluster of Docker containers. So that's what this runs as, is a Docker container. And with those Docker containers, you essentially all point them to a single node. So say I take node 1 through 5. Node 1 I can designate as the head node, and then, or the master node, and then everything else can be the worker node that will point to that head node. And what that will do is the head node then will kind of orchestrate how everything is working together. And essentially, you can spread then your one model across 5 different nodes. Instead of being tied to only a single A30, now we can leverage whatever that happens to be, 120 gigabytes, 24 times 5 of RAM, to spread a model across. That will allow us to run larger models, that will allow us to run models with longer context, that will allow us to do a lot of other things. And the upside to doing something like this is that we can use a mixture of experts model, and that will, in telling the LLM how we want to actually configure that, we can lock it down to where the experts, that mixture of experts, the experts all run on a single GPU. That kind of eliminates the issue where you have the model sending information between GPUs, that sort of thing, which can be very slow if you have an HPC like this one that was never meant to do something like this. So to go ahead and get started, what we need to first do, I have notes off to the side, and if you guys want, I can copy those into a GitHub repository with a little bit of walkthrough on how to do everything. But the first thing that we have to do is get into our HPC. So here, let's see, if we want to see if we run that, we can see all of the different nodes that we have here. So we have a bunch of them up. There's 75, or maybe there's a couple of fallovers, but we have all the nodes listed here with sinfo. What we first need to do is allocate some of those nodes for the work that we want to be doing. And today what I'm going to do is I'm going to use Qwen3, the 30 billion with the 30 billion parameters as the mixture of experts. And with the 4 GPUs, another thing that you have to keep in mind is that the models have information about how many, I don't remember what they call them, but there's like attention heads inside of the model. And the number of GPUs that you spread those across has to be a divisor of that. So say we have 10 head attention nodes, or whatever you want to call them, inside of the model. That means we can only use 1, 2, or 5 GPUs to spread that model across. It has to be a divisor. So Qwen 30 happens to fit across 4 nodes. So what we'll do is we'll start that here. We'll take and start with slurm a job with 4 GPU or 4 nodes, each with an A30. So to do that, we can do allocate. So SALLOC. We want nodes, 4 nodes, and tasks per node. I don't know, a job in which this and CPUs differing is too critical, but we can do here just a single one. And then GPUs per node, we only have a single one. But in the case of the machine learning cluster, say we have a handful of different nodes there, but each of them with 8 GPUs. Maybe a couple of those GPUs on a single node are being tied up. We can spread this across a few different nodes with this. So we can do, say, 4. If there's 8 GPUs, we can do 4, and then we can say we want 2 nodes. And then CPUs per task, we can do 4. So then each one of these nodes will give us 4 CPUs. And then just as like a kicker here, we'll do a memory of 40. This is not really all that important because we're going to leverage the GPU more than the CPU, but we'll keep those. And then time, we'll do 30 days. So 30-000000. And then on the cluster, so this is called red, we'll do red. And actually, before I do this, remember in the last video we had run, not in the last video, but the last compute video, we had learned about tmux. So what we want to do is do tmux new session, and then let's just run that. So we'll get a new session here. It's going to be called 0, but it should start up on our head node. There we go. Let's actually Control B and then D it to detach. I'm going to copy this command, that way I don't have to retype it. All right, so then tmux ls, we can see our different running windows. We'll do this one since we started it on August 11th. So tmux attach -t and then 2. So here we are inside of that 2. So we can go ahead and request this. So like I had mentioned in the tmux video, this is really helpful because what we can then do is close down our terminal session. In tmux, the terminal multiplexing will keep it alive in the background. Then we don't have to worry about trying to, I don't know, figure out how to keep the job running while we close our computer or shut it down, something like that. So we can go ahead. Need to spell out nodes instead of node. See if that'll give us the job. There we go. So now we can see here I have our 4 different nodes, 56, 57, 58, and then 59. which is great. Now we're going to do a few different commands here to prep everything up. So we'll cd into this directory that I have here. And to do that, we can do cd share lab superior and then dl. So this is my deep learning folder. If we do ls, we have the exact same thing here that shows up here, which is great. Now, the Docker container, like I had mentioned, that we use is vLLM. So if we do docker image, just to keep the variables, something that we can pass them to all the different nodes through the orchestration, we'll do it this way. And that lives at vLLM and then vLLM-OpenAI. So it'll have an OpenAI endpoint. AI, if I can spell it correctly. All right. And so then path to Hugging Face home. So this is essentially going to be inside of our container where our models are going to live. So we can do path to HF home equals, and then the same similar path with one more folder here. So we'll do share lab superior DL and then models. So that's going to be where our models live. Awesome. So then vLLM directory, I just have this for some logging. I don't think it's entirely necessary, but it's good to have some of that stuff that you can then go back later and see the metrics, say, for how fast the model is running. And I have this, it's in the same folder here, it's just in vLLM. So we'll do share /lab superior DL and then vLLM. So this guy, this purple one. All right. And then something that I've run across in some of the errors, I don't 100% understand what it's for, but it does help. Get timeout equals 300. So inside of all of these containers, it's running array cluster. And so happened when I was doing some of the models before, I think it takes a little too long in order to kickstart the model across these particular nodes, especially when I'm using the 235 billion parameter model. Just increasing that timeout seems to fix the issue. So I just happen to now have it as part of my code. All right. Now we're going to do a couple different commands. I'm going to copy and paste, but I'll walk through what they're doing. So let's go down here. So host names. What this is going to do, it's going to pull out the different names that we have inside of our slurm variables. So we do host names. Here we can see we have the first host name that is being run is 56 here, and we can see if we go back up, yes, we have 56, which is great. And then that's just going to be our head node as well. So if I run this command, head node, we're just going to pull the first value, head node. Cool. If we run this one, show host names. Let's try to echo this one just for experiment. There we go. So we can see all of our nodes there. It doesn't list it out, but if we do the host names of the first guy, that'll be what our head node is. So that's the only one that's really important, because what we're going to do is we're going to tell all of our different worker nodes, which are going to be the three other ones, to talk to HPC TPA3 PC0056 in order to find out what it needs to do. All right. Then we're going to export all of this stuff, including our slurm job ID, which is going to be the ID that was given when our job was granted. And that's going to be something that I use then to help log the information that the model is printing out. But we can see I'm exporting our Ray C graph, our vLLM directory, blah, 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 blah. And what this is going to do is it's going to tell Bash or Linux that we want these to be available to our environment. And then go back to tmux. And there is a way that we can exclude nodes. So we'll go here and we'll do -x HPC TPA 3 PC0058. And again, I have to spell nodes correctly. All right, there we go. So we got 7, 8, 51, and 52. Now let's see whether or not we can get her to run. So I'll just copy and paste some of these into here. Get all of our variables started again. So we have our Docker image, we want vLLM, Hugging Face home, that's going to be in our DL folder, our deep learning, and then we have our vLLM folder. You can hear the puppy rolling around on the chair mat. And then we have our host name, so this is going to give us likely 7. So let's go ahead and echo this. Echo. Helps if we put in a variable. There we go. So we got 7, 7, 8, 51, and 52. Then we can export all of our variable names. Wonderful. Then let's go ahead and do our trap. And the thing is, when you stop a job and then start it again, you have to re-put all of this inside. Otherwise, it doesn't know what you have previously ran. Now let's see whether or not we can migrate podman. There we go. So we'll delete any vLLM models that are present. And I had 2 of these nodes used before, 7 and 8, in order to host the same model, and the job had died yesterday or before. Now what we can do is pull the model, or pull the vLLM container, and this is going to take a little bit. The HPC is fairly fast, but some of them are large chunks. So I'll see you back when it is done. All right, now we have our containers downloaded, and we can see that we're on 4 different nodes here. So careful not to scroll in tmux because it gets into running, doesn't work like normal scroll. So what we can do is copy these here just to see. You can see that we have 1, 2, 3, and 4 different model containers being written to the different nodes. So that's 4 different nodes. Now what we can do is break down the next command. So let me go ahead and copy this. Actually, yes. And then we can look at what we got here. So what we have is we're going to srun, and then end tasks are slurm nodes. So let's go ahead and look at what we have here. So right now we can see that this had run successfully, and we have now an ID. So we have 4 nodes. So what we're going to do is we're going to run this command 4 different times, and we have the 4 different times, and once on each of our different nodes that we have. And we're going to run a bash command, and that command is change our directory to our vLLM directory. All right, so let's echo our vLLM directory. Okay, so we're in our share lab superior deep learning vLLM. So all of our nodes get changed to that directory. Now we're going to look at the host name and see whether or not that matches our head node. So again, echo our head node. If our host name of whatever node, remember we're doing it for 4 different nodes, if our host name matches our head node, i.e. for the one job or task that's being run on our head node, we're going to set the node type to head, and then we're going to start our array cluster on that node with head, and we're going to open the port for that. Okay, so that's our command in order to start our array cluster. Otherwise, so if we're on node 8 and 51 and 52, we're not going to match our head node. right? So our head node is 7. We're going to set our node type as our worker node. And then what we have to do in that case is we have to say ray start, just like before, but now we have to point that worker to what our head node is. And remember that we opened that port 6379. We're going to point them all to that port on our head node. Okay? Then what we're doing is we're going to echo out that we're starting our ray cluster on 7, and then our node type is going to be, or whatever the host name is, so it could be 7, node type will be head, or it will be 8, 51, or 52, the host name, and then the node type is worker. All right, cool. Then we can come down here, and what we're going to do is we're going to launch our podman, right? Because our vLLM is a Docker container. What we're doing is we're going to say we want our environment variable to be ray cgraph. So this then is the variable that we had set above. We might not need to export it, but good here just to reiterate what we have. We're going to remove the container when it shuts down. Remember, so this is the container, not the image, but we're going to remove the active container to try to just keep everything nice and clean. The entry point is going to be bash, so that way we can get inside if we really need to. Network is host, because the host name will map the IP address for 7. We're going to use all the GPUs. Now in our case, that's just a single GPU, the A30. The name is node, so like before when we were cleaning up our environment on all of our different nodes that we were running on, we had the container named node that was on a couple of them. We're going to set the volume, so -v is volume, path to Hugging Face home, so that was /share /labsuperior/dl and then /models. So this is inside of the container, going to be now found at /root /.cache and Hugging Face. So inside of Hugging Face, we will see all of these different folders, and we'll be able to run them once we get inside of the container. Then we're going to run the Docker image, which we had set to the vLLM /vLLM-OpenAI. And then inside of the container, we want to run a command. So I had noticed that when I was doing some of these things, that some of the Python packages are not always up to date in what's shipped. Now, if a model comes out and you're trying to run a new model that's GGUF, which has everything baked inside, it might be shipped before vLLM has had an opportunity to iterate its version. So we'll just upgrade that, PyArrow, pandas, so on and so forth. And then once we have all of those upgraded, we're going to start our ray cluster with ray start, and then whether or not it was our head node for running on node 7 or for node 8, 51, and 52, we're going to start pointing it directly to our head node, and then it will be all good to go. All right, and then this down here is what I was saying. Inside the folder, I'll just create this log. That way we can see every single iteration. Every couple seconds, it'll print out the token generation for the model, whether it's prompt processing or whether or not it's the actual response to whatever you had. Okay, now we are going to go SSH into our head node. And remember, that's going to be our 7. All right, here we go. Now we are inside of our head node, and we will want to go back, share lab superior DL. So now we're in that same folder that we were just inside of. I'm going to, again, set the vLLM directory. In this case, it's because I was doing some logs. Let's see. Yeah, doing some logs. So when I also start up the OpenWebUI in order for it to have the front end, it's really nice to have that available. And then we're going to do this guy. So this might be a little outdated, but in essence, what we are doing here is we're setting rope type to yarn, factor to 4, and original max position embeddings 32,768. So for the model that we're running, the original, when the first Qwen 3 30 billion came out, it had an original context of like 40,000 or something like that. If we use this rope type, yarn, what it's going to do is it's going to scale the context a little bit. So this is just what it had suggested. I don't know why this isn't 40,960 like the model's original context was, but they had suggested using this. And since we have our scaling factor of 4, we're going to have essentially 4 times this, 128,000, maybe a little bit more than that, 131,000 as our total context now. So this can be a really powerful thing. There's different rope types that are available. This is one that they had suggested. So we go ahead and set that. That's converting our model to only a 32,000 context model, now to a 131,000 context model. Just have to make sure that when you do something like that, the VRAM that you have available is supporting that context length. Now we can create a variable that will allow us to actually use that inside of our model serving call. So here, just create a new variable with the flags. So just like any command line, dash dash, rope scaling, and then we're going to paste in that JSON context. And the reason that I have this, our content, is if we were going to run it in like a regular slurm script, it would be a way to make sure that none of the quotation marks or anything like that break when we do this. Otherwise, you can just type everything out in the, I think you can type everything out, making sure you're watching where the quotation marks are and are not. So single quotes and double quotes to paste it all in a single command. All right, and then this next one will get us the actual command that we want to execute with our podman run command. So let's go ahead and echo this guy. Echo $. There we go. So we're going to basically echo or repeat back that we're starting our vLLM serve. So that's a command that we need to run. We can run vLLM serve, and then like I said before, inside of our model folder we have Qwen 330 billion extract blah 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 blah, this guy, and it lives now instead of at our control B, this guy, yeah, scroll up here, instead of at slash models. So this, I didn't have to scroll too far up. Models, now it's inside of our container, inside of our vLLM Docker container at root cache Hugging Face. But we still see that we have Qwen 3 30 billion, the updated model essentially that they had pushed out. And then we have tensor parallel. So what this is going to tell vLLM is that we want to run this model across 4 different GPUs. And there's a couple different ways to specify this, but I think it all boils down to internally being able to run tensor parallel size and then the number of GPUs that you want. Now we can say that we want the max context length of our model to be 131,072. So this is going to be how this line pans out. So we have 4 times our 32,768, which should be this number, 131072. Our API key is just something that we make up. What this is going to do is it's going to tell vLLM not to accept anything coming in unless it has this token. So this is what you can use and paste inside of your Python script if you're going to point to the API, or you can, I don't know, put it into your OpenWebUI if that's what you want, and say, okay, on HPC 3 PC 0007, HPC TPA 3 PC 007, that's where our model is living at port 8000, and the password essentially to get to the model is token-abc123. Awesome. Okay, so then enforce eager. This is something that I've had to use on the HPC where I'm running a model across many different nodes. I'm not 100% sure, but I'm not able to build the CUDA graph on here, but this is something that it just tells you to do if you have it failed to load. Enable expert parallel. So like I had mentioned at the very beginning, Qwen 3 is a mixture of experts model, meaning that inside of the model only, in this case, 3 billion parameters are going to be active at any given time. So while the model may be rather large, you can fit all of the experts on a single GPU, and that's what this enable experts parallel is going to do. Then we have our rope scaling again, just like up here. So I've hard-coded it in for this example, but it doesn't have to be hard-coded in. We can now echo essentially that command to execute. So this is the command to execute. Essentially, oh, yes, it is now coded in correctly. I'm sorry. So we have our rope scaling, again, type is yarn, factor is 4, and the original embedding length is 32768. So this together here now gives us the max length. And then our host, we're going to run it on the machine that we're currently on, and then the port that we're going to map it to is 8000. And that'll be something that then we can use later to, see if I can get back, to point at. So we would do HPC TPA3 PC0007 port 8000, and that'll point us here. If we don't have the API key present, it's going to say we're not allowed. When we do have the API key present, it's going to start accepting the incoming messages, generating the embeddings. It'll generate a response, or you can chat with it then. So then it will have a little bit different understanding of how to handle the message. All right, so then I don't believe, all right, so then the command, since we have our command to execute, we're on the node that is our head node, and I think you can actually do this from any of the nodes now that you have a head node designated, but we're gonna do it on the head node. We do podman exec, so execute node, so we're gonna execute inside of the vLLM container that we had started called node, and we can see that if we do podman container ls. Here we go. We've had a container running for 14 minutes and it's called node. So podman exec or execute on node. We want to do a bash command, so bin bash, and then see what command do we want to run. So we'll do quotes, and then the command to execute. All right, and then if we run that in the background, we can just do the ampersand. There's also ways with Docker to run things in the background, but if we go ahead and do that, now it's going to start spinning things up. Now we have a PID, I think that's what this is, for that. What we'll see now is we're starting up the container, it's going to run through everything, and then we'll get back to this when it's done, if it doesn't error out. All right, and we're back. So now we can see that we have essentially our vLLM container running. It is running at the location that we had set. So it would be HPC TPA3 PC 0007:8000. But what we can do, let's see if I'm able to attach into my container here. OpenWebUI, we can go ahead and go into here. We can see that the model that I had just started is running, and we can ask it a question. There we go. Now it has some toggles in here. This might be a different video, but what we have is all the different controls. We can set a system prompt. We can set our seed, so if we want some reproducibility. It's not perfect. I heard that there's always going to be some randomness when using CUDA, on the GPUs, which is a little unfortunate for research purposes. Then we can set the temperature. If we want something a little bit more consistent, we can keep it a little bit lower, so on and so forth. The OpenWebUI is outdated. It's been persistently running for a while. I need to just restart that. But otherwise, that's everything. Let me know what you guys think. Bye.